All right, so section 3.6 is about relations and functions, and these are tricky little vocabulary words because it's like a rectangle and a square. Like a square is a rectangle, but not every rectangle is a square. Same type of thing for relations and functions. So the formal definition of a relation is that a relation is a set of ordered pairs. The set of the first components in the ordered pairs is the domain. The set of the second components is the range. And it says here, many everyday occurrences involve two quantities that are paired or matched up with some rule of correspondence. And a relation usually looks like something like this. So a relation is any set of ordered pairs. When you see these fancy brackets, it's just a fancy notation for showing that this is a set of numbers. So if I said graph this relation, that means just graph the set of ordered pairs. You would graph 0, 1, 1, 3, 2, 5, and so on. But in these sections, they're going to ask us to find the domain and range of the relations. The domain is the x values. The domain is talking about x values, and the range is talking about y values. Sometimes the domain might go on forever and ever. If I said, what's the domain of the equation y equals 2x plus 1? The domain would be any x number that you could use, and sometimes it goes on forever from like negative infinity to positive infinity. Sometimes the domain will just be listing numbers. The domain of this relation, since this relation is 1, 2, 3, 4, 5 ordered pairs, the domain of this would just be the 5 numbers that are in the x spot. So the fancy way to write this, and I am going to ask you try to do this, just because you'll be getting yourself prepared for higher level math courses. Yeah. That's fine. So 2 options. You can either write this down and then copy it over, or watch this later and write it down. Up to you. I wish I had another copy, but I don't. So the domain is going to be, the notation looks like this. A capital D for domain, and then you use a colon, and then these fancy brackets. And then you just list all of the numbers that are in the x position. So that means the x coordinate of each ordered pair. So the domain would be 0, comma 1, comma 2, comma 3. And then actually 0 occurs again. So I don't have to include that a second time because I already did when I wrote 0 the first time. So the domain would be 0, 1, 2, and 3. You're supposed to write these in order from least to greatest. They were kind of already in order from least to greatest until that second 0 occurred, which you don't have to write a second time because you already included it the first time you wrote it down. But I'm not sure how picky I'm going to be. All right, and then the range. Same type of notation. You would use an R for range, a colon, these fancy brackets, and then you list the numbers in the range spot, which are the y values. Again, you're supposed to list them in order from least to greatest. I see 1, 3, 5, 5 again, and 3 again. So the numbers that occur, and it doesn't matter how many times, the numbers that occur are 1, 3, and 5. I do not need to write 5 again or 3 again because I already included them when I wrote them the first time. So there are 4 numbers that happen in the x spot. There are 3 numbers that happen in the y spot. Every single thing we see in algebra when it comes to graphing, or it comes to ordered pairs, or it comes to a table, everything we've ever seen is always considered a relation. You just never hear me call it that. But not every single relation is a function. So a function is a relation in which no 2 ordered pairs have the same first component and different second components. For instance, 2, 3 and 2, 4 could not be ordered pairs of a function. And here's why. We already talked about in one of the last chapters that when you have 2 numbers or more that create a vertical line, those lines don't have slopes. They're considered undefined slopes. And that's because these things turn out to be not functions. So if I was to graph the points 2, 3, and 2, 4 just on this sketch here, here's 2, 3 would be here, 2, 4 would be here. I can quickly see that these 2 points are on the same vertical line. And every vertical line that we always see in algebra, we know does not have a slope that exists. It's considered undefined. Anytime you have any points that are on the same vertical line here, it creates it makes that relation not a function anymore. Because this is undefined, you would consider this to not be a function. It would just be a relation. So just like how I said in the beginning, the square and rectangle thing. So a square has 4 sides. All the sides are equal. All the angles are 90 degrees. Every square is a rectangle because the definition of a rectangle is that there's 4 sides and 4 90-degree angles. But if you flip it around, not every rectangle is a square, because in order to be a square, not only do you have 4 right angles, but you have to have 4 equal sides as well. Same thing happens with a relation and a function. Every function is a relation, but not every relation is a function. We see functions all the time. Every time we put anything into y equals, that is a function. Whenever you have something that is a function, you can put it into your calculator. It starts with y equals. You see the graph, and the graph doesn't ever have any of these vertical lines here. If you ever have a vertical line, it's considered not a function anymore. So the next examples are trying to help us figure out if these things are functions or not with these examples that are all different. The first one is just like a random thought-provoking question, not necessarily math. It says, the input value x is any of the 50 states in the United States, and the output value y is the number of governors of that state. So you would have to know that there are 50 different states, and how many governors are there per state? 1. Okay, so we have all the different states, and all of these states have 1 governor. Now, if we were to graph this, let's say, we would graph every state separately, and all of these states would have exactly 1 governor. So when I'm thinking of that, if x is representing all the different states, and y is representing how many governors that they have, this would create a horizontal line. Because if we were looking, I know we can't, if we numbered them 1 to 50 instead of by their name, if we numbered them 1 to 50, then the first state would have 1 governor, the second state would have 1 governor, the third state would have 1 governor, and that would create a straight horizontal line. Horizontal lines are okay. Horizontal lines are considered functions because they do have real slopes. So deciding whether or not this represents a function, letter A would be a function. And that's because if we were to graph this would create a horizontal line, which is okay. The only time it's not okay is if it's a vertical line. Letter B, looking at this relation, I see a set of ordered pairs, 1, 1, 2, 4, 3, 9, 4, 16, 5, 25, and 6, 36. To determine if something is a function or not, you have to decide if any of the x values repeat. If they do repeat, it's not a function. If they are all different, it is a function. So I see 1, 1, I see a 2, 3, 4, 5, and 6. None of these numbers repeat. So if I was to graph these points, none of these points would be on the same vertical line. Because of that, letter B would also be a function. But once I get down to letter C, this is the first one that's a little bit different. I see -1, 7, 3, 2, 4, 0, and 3, 4. If I were to graph these points, where would I see a vertical line at x equals what? Four zero would be on the x-axis. I agree, but it wouldn't have a vertical line there. At 3, yes. Why do we have an issue when x equals 3? What happens when we have x equals 3 in this situation? It has 2 y values, right? So right here is where we have an issue, 3, 2, and 3, 4. If I was to just graph a sketch of these and say this is -1, here's -1, 7, here's 3, 2, 4, 0, and 3, 4. Right here, I would have an issue because you can never have 2 points vertically. If you have ever 2 points that are vertical, that makes that relation not a function anymore. It's only considered a relation. So letter C would be just a relation. Now, every single thing is a relation. So I could say letter A is a function and a relation, a function and a relation. This is just a relation. But you don't have to necessarily call everything a relation because it just is. It's more important to call it by its most specific name would be a function. All right, and then letter D is giving us kind of a weird situation. They're saying let's set A, be A, B, and C. So they're giving us a mapping diagram, it's called. So A, B, and C are here in the map on the left-hand side for A. And it says B is equal to 1, 2, 3, 4, 5. So we see 1, 2, 3, 4, 5 in the mapping diagram. And we're seeing a couple things go on here. We see that A goes to 1 and A goes to 2 here. We see B goes to 3 and B goes to 4 and C goes to 5. So if I was to make a table of this, and instead of using X and Y, I use A and B. A on the first one here goes to 1, so this would be like A1. But then A also goes with 2. B goes to 3, and B also goes to 4, and then C only goes to 5. I know we're not using X's and Y's here, but if we thought of the capital letter A as X and the capital letter B as Y, I see two issues with this because there are 2 times that the X values repeat, and it happens here, and it happens here. Because of that, I would have 2 different points in the graph that would create vertical lines, which would make this thing not a function. The only thing this is a relation. Does anyone have any questions on that? You're basically only looking for the X values. If they repeat, it's not a function. If they all are different, it's a function. All right, the next section, which is or the little part of the section, which is all over the place, is asking which of the following equations represents y as a function of x. So that means which of the following equations are already in the form y equals, or could they be in the form y equals? Sometimes it might not look like it, but sometimes you can take it and change it around so that it is in the form y equals. So looking at letter A, it's a given. I mean, we can already see that this equation is y as a function of x, because to figure out what y is, we would take a number in for x, replace it in, square it, add 1 to it, and we get y out. So which of the following equations represents this? This one does here, so I'm just going to circle it. This one does. And let's move down the line. Letter B. So letter B is a little bit weird. It says x minus y squared equals 2. For this type of problem, in order to figure out if it is a function of x, you have to first think to yourself, does it say y equals? If it does, it's automatically yes. Because every function we have can be put into a graphing calculator, and it has to start with y equals. This one doesn't say y equals. It says x minus y squared equals 2. So the next thing to decide if this can be a function is figure out, can I easily solve this thing for y? So if I was to solve this thing for y, knowing what I know from before, I would subtract both sides by x. I'd be left with negative y squared equals negative x plus 2. And then I'm kind of stuck. And the reason I'm stuck is not necessarily because of the negative y squared, the negative y. Like I could divide everything by negative 1 and everything will be good. But what's really the problem is the y squared part. Like if I said put this in your calculator, you wouldn't really necessarily be able to because of the y squared. And because of that, this one is not directly a function of x. All right? But letter C is a function of x. It does not look like it, but the way that this is currently it's in a form that we know from previous. It's called general form or standard form, and even though it doesn't say y equals, we could quickly take this and solve it for y equals by adding 2x to both sides and then dividing by 3, and we would get y equals 2/3 x plus 4/3. Because we can quickly solve this for y, that means that this is a function and that y is a function of whatever x is. So this one would be a function as well. The only time you don't have functions is when you can't quickly solve for y. If you can't quickly and you're stuck with like y squared or y to the 3rd power, Now you can like take the square root of it, but it becomes tricky, and these equations are actually like circles, and when you have something like that, you repeat the same type of x numbers, which makes a vertical line. Okay. So moving on to the next page. Because of time, we're going to skip A and B. They're just kind of like silly problems about things we don't actually have to worry about for our next test. So we're going to skip right to the next part that's really big, which is function notation. So function notation is a way that we write down equations and functions instead of y equals. So we're used to, especially from the linear equation and linear inequality, we're used to seeing y equals, and then maybe like a linear equation could be like 3x plus 4. We're used to seeing this in this notation. This is like the normal notation we use with graphing calculators. This is the normal notation we use for slope-intercept form. This is typical for us. Function notation is a different notation that's used primarily for these types of sections. They're used in higher level math courses like calculus. You'll start to see these a lot. And the way that the notation looks is this. So it's like the letter F, usually the letter F. It can be any other letter, though. In this example, we have G. But it's any letter, and F in this case stands for the function. And then it says parenthesis x. The way that you say this out loud, it's read out loud as f of x. So when you hear me say f of x, that's what I mean. It's not necessarily f times x, which is confusing because it looks like f is being multiplied by x, because we have f parentheses and x is on the inside. But when I read this out loud, I know that this is a function notation. One way I know that it's the function notation is this fancy f that they use. This fancy f is showing me that it is a function of x. So I would read this as f of x. The notation f is naming the function. It can be any letter, though. It could be G, it could be A, it could be anything but x, really. And x is the domain or the input value of the function. And then when you solve it, you get the range. So basically, this stands for x, which it already is x. And then the letter on the outside really is standing for y. So x is still the input. X is still the number you would replace in. And then the f part, the function part, is whatever y would it actually be when you put x in and you solve it. So the way that this works is for every function, they're going to give you some sort of equation that goes along with it. So this equation they give us is g of x equals 3x minus 4. Now we would used to see in the last section, instead of saying g of x, it would just say y equals 3x minus 4. And you might be thinking, well, why can't we just use that? That's way easier than this whole g of x thing. And I agree. This is just the way that the notation works in higher level math courses, and you guys are getting up there, so we have to understand this notation. So the way that these problems work is they're going to ask us to solve a problem, and you have to understand what it's saying without it saying much. This problem says g of 1. This means find the value of the function when x is equal to 1. Because 1 is in the x spot here, that means take the function g of x equals 3x minus 4 and replace 1 in for x and see what the function equals, which really means just take the equation, substitute 1 in, and solve. So when we replace 1 in for x, we would just do 3 times 1 is 3. 3 minus 4 is negative 1. So when we put 1 in for x, we get negative 1 as our answer. So the answer to this would be negative 1. The ordered pair for this means what ordered pair could you graph on the graph if we were to graph this function. And what we would do is use the x value, which is 1. This is what we replace in for 1. That would be your first point here. and then the answer is -1. So the ordered pair that we could graph is 1, -1, because when we replace 1 in for x, the function spits out a -1 for y, or in this case, g of x, they're calling it. So letter B is very similar to this. Why don't you just take a minute and try letter B? All right, so for letter B, we're taking this function, g of x, and we're replacing a -2 in for x. So when we do that, this is going to say g of -2 is equal to 3 times -2 and then -4. Now we would just solve this. You rewrite the whole notation the way that it is, the g of -2 like that, and then 3 times -2 is -6. -6 minus 4 is -10. So if I asked you then what is the ordered pair that you could graph, this would be -2, -10. So the first two are very similar, and then once we get to C and D and E, things start to change. Yeah?
On a test, would you want us to write out that OG -2 thing?
It depends on the type of question. So if the question said what is the ordered pair, I would want the ordered pair. If it says just what is the value of the function, the value is just -10. All right, so the next one says g of y. So this is saying take the function g of x, and in for x, we're going to replace it with a y, which just gets very confusing. So we're going to take the situation named function g of x, and instead of having x in there, we're going to replace the value with y. So it's going to say g of y equals, and then just instead of having a 3 times x here, this is going to be a 3y. And that would be the answer to letter C. There's nothing else I could do with that because we don't know what y is. We're just replacing y in there. So that just really just changed the variable that we would be using. And then letter D and letter E are going to get even more crazy. So I'm going to give you a second to write this down, and then I'm going to erase so that I can use some more space for D and E. So as we're going through these, they're getting a little bit more difficult. We just started replacing numbers in. Now we're replacing different variables in. And then in letter D, we're replacing an entire expression, x plus 1, in. And this is definitely getting to be higher order or higher level math content, which is kind of cool. So for this function, the function, let's remember, is g of x equals 3x minus 4. They want us to replace an x plus 1 in for x now. So that means I'm going to replace it here, and I'm going to replace it here. So the function is going to look like this instead. It's going to say g of x plus 1 equals, and then where I see an x on the right-hand side, I'm going to replace it with an x plus 1. Oops, not plus 4, minus 4. And I have to make sure that I'm using the parentheses still because it is the entire thing x plus 1. Then when I would go to simplify this, I would have to use my previous knowledge of the distributive property to get rid of the parentheses. This would say g of x plus 1 equals 3x plus 3, and then minus 4. And then I could simplify this further to being g of x plus 1 equals 3x, and then 3 minus 4 is negative 1. So this is the first time the answer is another expression. There is no just answer. Well, I guess letter C was as well, but there is just no answer. Like for the first two, we were able to write ordered pairs and show you that this was x and this was like what y would be, the output. But this one, this is the answer. It doesn't look like it's simplified. It doesn't look like it's necessarily right, but this is correct. This is what the answer would be for x plus 1. And the last thing that we can do with functions is we can find a function by replacing a number in for this x, a number replacing in for this x, and then you can add them together. So in letter E, they want us to find what the function would be when we replace x in, and then what the function would be when we replace 1 in, and then we're going to add these two final answers together. So what's interesting about the first one is g of x is just like the original thing. G of x is really equal to 3x minus 4. And I know that because the original problem says g of x equals 3x minus 4. So the answer to this part of it is 3x minus 4. But then we also need to find out what g of 1 is, and then we're going to add it to 3x minus 4. So g of 1 would mean actually take this function, replace 1 in for x, which we already did here, so we already have this answer, but we could just do it again. And 3 times 1 is 3, minus 4 is negative 1, so I know g of 1 equals negative 1. So if g of x equals 3x minus 4 and g of 1 equals negative 4, we're taking these two things and we're adding them together. I'm only putting the parentheses around just to show you that I'm taking these two things and adding them. When I add these two things together, I can combine like terms. 3x does not have anything to be combined with, but I can add a negative 4 plus a negative 1. Altogether, that would be a negative 5. So altogether, this answer would be 3x minus 5. So altogether, this would equal 3x minus 5. Okay, the last thing that we have, and this will be the last thing for today, is this piecewise function. This piecewise function says, depending on what x is equal to, you will have a different function for what f of x is equal to. So that means that for these problems, anytime x is less than 0, if we were replacing a number in that's less than 0, we would have to use this function here. So looking at these numbers, let's figure out the numbers that are less than 0. Negative 1 is less than 0. Is 0 less than 0? Nope. Is negative 2 less than 0? Yes. Is negative 3 less than 0? Yes. 4 is not. So for these three little parts, we would be using the function x squared plus 1. And then for the other ones, it says when any time x is greater than or equal to 0, you would use x minus 2. So we would use x minus 2 for b, since exactly 0 would be that, and we would use it for f of 4. So we're using two different functions depending on what x is equal to. So for the first one, it says f of negative 1. We're going to be using the first function, which is x squared plus 1. So to solve this one, f of negative 1, we use the first piecewise function, which is x squared plus 1, and I'm replacing a negative 1 in for the x squared. Negative 1 squared is negative 1 times negative 1, which is 1, and 1 plus 1 is 2. So this whole answer here is going to be 2. So a is equal to 2. Then b, I'm going to be using this other function, the blue one, because x is greater than or equal to 0. So I would use this one, x minus 2. So to find this one, this would be f of 0 equals, I replace in 0 in for x, and we're going to get negative 2 as this answer. So depending on what the x number is, you have to decide what function to replace that number in for. So I want you to try C and D. C, you just put it in the right function and then solve. D, you have to use two separate functions and then add those final answers together. So I'm going to give you a couple minutes to just try it, and then before we leave today, I'll go over it. Bless you. All right, you might not be done both, but I want to make sure I can go over it before the end of class today. So for letter C, f of -2. So x, the number we're replacing in for x, this -2 here, since it's less than 0, I would use this function right here. So I'm going to be using x squared plus 1, and I'm replacing in a -2 in for x. So this is the function I would use. F of x equals x squared plus 1. So I replace in a -2 in for x, and I solve. -2 squared is 4. 4 plus 1 is 5. So the answer to this one is 5. For letter D, I'm going to be using two different functions. -3 is less than 0, so I would use x squared plus 1 for the first one. So f of -3 would be equal to -3 squared plus 1. I would solve that first. -3 squared is 9. 9 plus 1 is 10. So I get that one of these answers is equal to 10. And then for the other one, since f is equal, or f of 4 means that x is greater than or equal to 0, since 4 is greater than or equal to 0, I would use this one here. So for f of 4, I would be using x minus 2, so this would be 4 minus 2. F of 4 is equal to 2. So if f of -3 is equal to 10, then I would replace a 10 here, plus if f of 4 is equal to 2, I would replace a 2 here. The final answer to this whole entire thing is 12. So it's tough stuff. It's definitely going to be getting interesting now that we have all of these different components.